Hello. Hi. My name is Sanna, and I'm going to be presenting purely relational data structures. This is joint work between myself and my advisor, not Amin and Byrd. Before we jump into the actual data structure stuff, I'd like to start with kind of the impetus for some of this work. Who here is, by just show of hands, has seen this textbook before? Okay. This project actually started when when Byrd wanted to go through this textbook and implement as much of it as possible in miniKanren'. Spoiler warning for those who have not read the first chapter. We don't get very far, so you don't. If you haven't implemented all the exercises in chapter 14 on dependent object types, you're still good. But specifically, the issue that we ran into started around here. So this is one of the first definitions in the entire book, and it literally defines simply typed untyped lambda calculus terms, right? So we kind of define it intentionally. Specifically, that term intentional being quite important, so I'll take a second to explain. Intentional here means that rather than list out all the possible elements of the set, we give it the defining properties that are necessary to be a member of the set, and sufficient as well. So here we give kind of a traditional smallest set fixed point definition. We say for all terms, here are the ways to construct it. You have the three kind of canonical ones. You have variables from some countable set of variable names, lambda abstractions, and applications. I imagine this is pretty bog standard to those who have seen it before, or even those who haven't. So this set is obviously infinite. There are an infinite number of lambda terms. And so intentional definitions are the better way of specifying something like that, because we can't enumerate an infinite number of possible terms explicitly. So translating this into miniKanren' is relatively easy. I imagine that this definition is going to be relatively canonical to those who have seen miniKanren' before. It matches pretty much one-to-one with the definition we saw on the prior page. And this works out well because, again, this is an intentional definition, and miniKanren' is very good at these. It's able to give us, this is the necessary conditions for defining sets, defining lambda calculus terms. It's the kind of least set model that was brought up here naturally kind of models the Brand terms logic that is used in the smallest Brand universe used by the semantics of logic programming. So this, I think, kind of has a natural dual with for making sense of why this is kind of very easy to define. So it's this definition where we start running into a bit of a problem. So this definition defines a set of free variables of a lambda term. And so what's important about this lambda term is that with respect to a given, what is important about this definition is that with respect to a given lambda term, the set of free variables is defined extensionally, meaning we list exactly which variables are part of it. And so this set is also finite for a finite lambda term. So you can see we do some basic set operations using a singleton set, the set union operation, etc., the set subtraction operation, which is written with that / symbol. The fact that this is finite is rather important because, as again, bit of a spoiler warning, it is very important to be able to tell whether or not a term has no free variables because it's how you define combinators. So trying to define this in miniKanren' is not impossible, and this is probably my best bet on how to do it. So you can see that we can't define it in the way we did before, where we just have the intentional definition. We have to explicitly reify the set of possible answers as this free variable value. Why is that? Because it would be very different, because as is well known in the logic programming community, having negation, or saying there is not a free variable, is rather difficult to define, especially for intentional sets, because that gets into a long list of classical issues with have to do negation. So defining the sets extensionally is the best way to kind of get this negation effect by saying there are explicitly none. And so I highlighted in blue the set of constructors that I'm using here. So notably, we're using set unification, a set constructor, and so then that is a procedure defined at the meta level. This is in the same sense that cons is defined at the meta level, or list is defined at in the meta level in miniKanren'. And we use subtracto and union O, subtracto being subtract out an element from the set, union O being union, as is, I imagine, to be expected. So I think other than the kind of operations here, this should be relatively straightforward a translation as well. Anyone have any concerns about either of these translations? Great. So the question then becomes, how do we define these constructs? So one way you might try defining these constructs is using the kind of classical Lispy way of defining sets, which is just as lists. So we define the set constructor to just literally be the list constructor. So the set of elements 1, 2, 3 is literally the list of elements 1, 2, 3. But then, because lists also have duplicate elements and consider ordering, we need to have our own notion of unification, which is this set equal equal on the bottom here. This is defined in terms of a subset eco operation, which is just the inclusive subset operation. This is a relatively canonical inductive definition of this this relation. It is definitely a correct implementation. It is naive in the sense that we have to like bear a linear time cost for checking whether or not something is a member or not, but otherwise this seems relatively reasonable. The problem arises when we try to actually use it. So in this case, this is a technically correct answer, as I mentioned before, but procedurally and operationally, we end up with a lot of issues. Specifically, we begin enumerating all possible sets in the same equivalence class. So on the top here, you can see that this free variable example just immediately begins enumerating all the quote-unquote equivalent versions of the same singleton set X, because, again, we told it to ignore duplication here, but it's still searching over the number of possible duplicates in the set. You can also see that we get multiple versions of two sets because it's implicitly reordering the same element, which of course isn't meaningful. And we can see why this happens if we look at a simple unification on the second line here. When we are trying to unify a constant set against just a fresh variable, we actually begin enumerating all possible sets in the same structure. And we can see, again, we are considering all possible sets with respect to ordering and with respect to duplicates. So this isn't a time complexity issue. I'd like to stress that quite a bit. This is a fundamental usability issue. It's not tenable to do this kind of work because A, you destroy any chance you have a finite failure, which is generally something miniKanren programs should have, and B, it entirely destroys your backtracking because now every time what would normally be a singleton result and would allow the miniKanren search strategy to move towards a different branch of the search tree will now infinitely enumerate these, and while the search is complete and will eventually find the answer, it will just be significantly slower. So how do we fix this, right? You might think, okay, sure, using lists like this is incredibly naive, right? This is like not how anyone who has a good understanding of data structures would implement a set. Maybe there's just some different data structure that we need to use. And so we might turn to kind of the Bible of data structures in functional programming land, PFDS by Okazaki, as kind of a way of defining these in a new method. So Okazaki, this work was really important for a number of reasons. Not the least of which being that all of these data structures were defined in the language at hand, where they didn't need to add much to ML or to Haskell in order to get these data structures to come out naturally, other than some slight laziness syntax, which hadn't quite been standardized. So while it may just seem like, oh, we need to get a better data structure, I'm going to claim that that's not true, is what we need is purely relational data structures. And that relational programming needs something that functional programming doesn't. So we need stronger notions of equivalence, and we need good search semantics. These things aren't satisfied by current data structures. And so there becomes a question of what do these data structures look like, how would we use them, and how do we find them in the real world? So one way we think this might look like in the real world is something like the work of setlog. So this is an implementation of specifically the set data structure by Dovier et al., which that lab has a long history of work of doing kind of this finite set semantics in Prolog. So specifically the language they use is called setlog, and it defines a set of operations that crucially work as constraints rather than traditional inductive relations. So rather than mandate the data structure be in some specific structural form, it instead mandates it have some semantic form and not search over the possible structural forms that inhabit that semantic equivalence class. So can we port this to miniKanren'? The underlying logic behind it looks like something like this. Crucially, you'll notice a lot of the common operations that we have in miniKanren', disunification, disjunction, conjunction. It also has a universal quantification, that for all symbol, but pivotally, it is always for all x in some finite set. That ensures that we're never going to have the problem we had before where we begin enumerating all possible sets. If we were able to have for all x blah for any value of blah, then we would have the issue we ran into initially. So what do sets look like in this world? So here is the three kinds of sets that are defined in Dovier and how we represent them in Scheme. So the empty set is just written set here. This is the set which contains exactly 0 elements. As you saw in the axiomatization, it is defined to be an instance of a set. It is defined to have no members, and so on. The other object we have is the proper set. So this is a set which contains the elements A, B, and so on. Because this is a logic language, we aren't able to tell exactly whether or not A or B are distinct objects at a given period of time, right? One of them might be a fresh logic variable, or worse, two of them might be fresh logic variables. And so we have to kind of accept that there will be potentially be duplicates in our set. And this last implementation is an improper set, hearkening back to the kind of scheme language of improper and proper lists, where the rest of the set is some other fresh logic variable here R. And so having these three different ways of defining things allows us to implement sets in a way that give semantics to sets in a way that seems like it makes a bit more sense. So here are some examples of unifications using this method. So here we note we don't use a set equal equal operator. We are using literally just the normal miniKanren' unification operator. It understands sets implicitly. So we have at the top just defining to a fresh logic variable does the same thing you would expect it to do in any miniKanren' implementation. You just immediately assign it to the fresh logic variable and move on. Unification, even against sets that are semantically the same but are structurally different, will instantly succeed, as you'd expect. And an important note is this last element here. I apologize if this is a bit hard to read, but what this says is find all Q such that the set 1, 2, 3 unifies with the set 1, 2, and all elements of Q, set P, sorry. P such that 1, 2, 3 elements unifies with P. And pivotally, it gives us several responses back. Because we're not able to know whether or not P is actually contains the elements 1, 2, or 3 yet. you know it must contain at least 3. So 3 is in all of the possible results. But we know that 1 and 2 could possibly be in there, and so we enumerate the power set of 1, 2, 3 for all that contain 3. Does this sense of unification make sense to everyone? Are there any immediate questions? Great, we can move on a bit more. So unification is not the only set constraint that Dovier defines. So specifically, there is a relatively long list of set constraints, but they are defined in terms of these 3 primitives at the top here: non-membership, disjointedness, and set union. So set union we saw earlier as just the union of A and B is C. Non-membership is just the element is not a member of the set, and disjointedness is that these 2 sets have no shared elements. I won't go through all of these, but the key idea is that if we have these 3 primitives at the top, it's shown that we can express the rest of the typical set primitives that we expect in a set library or your favorite programming language. So, for example, here, union plus O is the disjoint union, which is, sorry for the large text. Here we just mandate here that for any L, R, and C, or 0, 1, and 2 in the fresh logic variables, they are all sets, first off. Next, that the first 2 are disjoint. That's what that parallel symbol means. And then the union subscript 3 means that these 3 should union to each other. And that's just kind of the definition of disjoint union. So if we use this way of defining sets, we get our free variables example to work as we would expect before, where we get back a single result. And again, I cleverly defined the set of primitives before as exactly the ones that are defined by CLP set, so it kind of works without any modification. So the initial implementation of this work was done by Nada and follows the implementation not of the actual software that is done by Dovier et al., because they have a software artifact that goes with it, but this actually implements the rewriting procedures. So specifically something like this. This is obviously you don't have to grok all of this, it's essentially how we define equivalence. So this is a way of turning the left-hand side, which is some primitive notion of equivalence, into the right-hand side, which are smaller constraints that have to do with it. And so by breaking it down, you kind of get down to the atomic constraints that we all know and love from miniKanren and can solve those normally. This is that unification procedure reified as code. I understand Scheme is like not a golfing language, but it's still quite a bit of work. And again, this is just unification. So the other set constraints are all additional code on top of this. So the impetus of this project was that we wanted to implement the CLP set operations in terms of Michael Ballantyne's faster miniKanren. If any of you have used a miniKanren in Scheme, or I think oKanren is similarly based off of a lot of the work by Michael Ballantyne, this is kind of the canonical modern implementation of miniKanren. It has a number of fancy features, to-watch literal scheme, a more efficient data structure for element lookup and environments, a whole bunch of very nice stuff. But there are some issues that arise with it. So going back to our definition of equality here, we can zoom in on a specific one of these rules, specifically rules 9 and 10. These are how we define unification against sets. And so the pivotal point here is that there are 2 things that we normally wouldn't think of as unification results. Namely, if you look at these, that keyword any of means it's a disjunction. So unification can now cause multiple results, as we saw before, which is kind of violating one of the typical assumptions we make about miniKanren as a language, that unification will either succeed at most once or fail. And note also that we introduce a fresh logic variable here, n, and we put a constraint on it. So unification is no longer just a function from finding the most general unifier. There is no most general unifier in this case. we have to give unification an arbitrary level of computation. This kind of causes some fun issues with some of the optimizations that happen in faster miniKanren. So we can see an example of this here. So here we're unifying two sets which contain 1 and 2. P and Q are fresh logic variables. But note that _0 is found in the results here. _0 is not P or Q. This is a fresh logic variable that was just introduced by the unification, and we bind a set value to it. And so if we have something like the two-watch literal scheme of faster miniKanren, which requires that unification always just become a conjunction of primitive assignments, then that no longer works. And it requires quite a bit of kind of hackery in order to get back a lot of those semantics. So in the paper, we kind of go over a lot of these things. We add, in addition to Dauvier's existing constraints, some association list constraints that allow us to do environments in the kind of typical Byrd-style relational interpreters. We face off against that that two-watch literal scheme idea within the disunification by using the first-order representation and optimizing it out in certain cases. We give a more idiomatic API for miniKanren and for set-based tabling, along with a few other things. But I guess this is where I will end things. The key points being that purely relational data structures improve the operational usage of miniKanren programs. They have to be reasoned about semantically rather than structurally, as we saw. They have to use lazy constraints rather than recursion. They can be implemented in modern miniKanren implementations, but challenge assumptions about what miniKanren is and how it operates. That's all I have, if there are any questions.
Questions you have? We have several minutes.
Great talk, cool stuff. I think I recall in the Dauvier et al. Paper, they talk about not just that choice of 3 primitives. One of those Dauvier et al. Papers, they talk about the choice of these 3 primitives as opposed to alternate options. What happens if you did this? What happens if you did that? Is there any interesting thing to say about how that differs in the miniKanren context or alternative choices, what that would do to the implementation strategy in faster MK?
So there were a few other methods that were considered by Dauvier. We didn't, they did not implement those other methods, and we didn't either. It seems pretty natural that the methods that we used for implementing them would translate over to the other ones. I'm not sure if they would give better operational behavior or better algorithmic behavior. It doesn't seem like that would be the case, at least. But I guess if there is reason to believe that, then it seems like we would naturally be able to translate this stuff without much difficulty.
All right, we have time for one more.
So you talked a lot about sets, but if you think a little bit further ahead in that, well, probably the more important data structure is finite maps for representing things like environments or stores, etc. So I was wondering if you had any thoughts about some case studies to finite maps, or if that's anything to say about that.
That's a great question. So in the paper, we actually do extend the work to specifically association lists. And so this is a kind of different way of talking about the data structures in general, where here we were using sets as kind of an abstract structure, but we consider a different way of doing things where we define association lists inductively in terms of their elements. Obviously, association lists are well loved by miniKanren programmers, but they do have limitations in that they put certain They make certain structural assumptions about the way things are ordered. And so I think natural next steps are extending this to things like finite maps and other data structures. And I think the more general next step is finding out how we can define these without baking them into the interpreter, right? Because these constraints now must be implemented as primitives in the interpreter. And so if we want tries or maps or any other abstract data structure, it requires some method of doing this encoding, And it's not sustainable to just write a new miniKanren implementation every time you need a new constraint.
All right, thank you for the questions. I think we are out of time. Let's thank the speaker. Thank you, Rafi.